we are discussing boundary value problems in ordinary differential equation. And in this lecture, we'll talk about the finite difference method to solve ordinary differential equations boundary value problem. The basic idea of finite difference method is that we first discretize the domain. So here in this example, the domain goes from z equals 0 to z equals 1, and we discretize this domain between 0 to 1. After discretization, we write the derivative in the discretized domain. Once we do so, as I'll show you shortly, this ordinary differential equation will be converted into a set of algebraic equation Ax equals b type, and then we should be able to solve this Ax equals b type equation using any of the methods that we have discussed before. So let us see how we do so. Just as a recap, the boundary value problems in ordinary differential equation usually takes one of these two routes. First method is the shooting method that we have already discussed. Shooting method converts the boundary value problems to initial value problems. Of course, within these initial value problems, we don't know all the initial conditions, so we have to guess the unknown initial conditions. Then, from those unknown initial conditions, we have to shoot the target BC, the boundary condition that is given to us. And to shoot it properly, we have to update the guess initial condition. At the end, our initial condition will be such that the target boundary condition is achieved, and at that point the shooting is closed. As opposed to this technique, we have now finite difference technique. Here our goal is to convert boundary value problem to a set of linear equation Ax equals b type, and then we solve them. In general, we use iterative methods, but we'll come to those things later. Finite difference method is more general than the shooting method, and in our discussion of partial differential equation, we'll use this method heavily. To understand how this method works, we'll take up a physical problem. We'll first model it and we'll discretize the equation, and then we'll solve the equation. So let us take up a simple physical problem of heat transfer. In heat transfer enhancement is something fundamental to most technologies. For instance, if we have an engine of a motorbike, we know that there is a chance of overheating, and that is where we use these extended surfaces at the engine. These extended surfaces will increase the heat transfer area, and overall heat transfer will be increased because of that. The same thing happens in a computer chip. You will see this long fins once you open up your desktop computer, and these fins are being used to keep the temperature within the prescribed limit. How do we analyze such fins? If you have already taken a course in heat transfer, then you already have the idea that what is the simplest way of analyzing this fin, and we'll not go very deep into it, but we'll solve the equations. Let us take up a very simple fin. This is a one-dimensional case, or if you have taken a heat transfer course, you know that this is one-dimensional but lumped case. So the fin here goes from x equal to 0 to x equal to L, and at the base of the fin, that it is at x equal to 0, we have a constant temperature T0. The outside ambient temperature is given by T infinity. So the fin here is used to keep the temperature within limit of an object that we see here. The governing equation of this fin can be developed using energy conservation over a infinitesimal area here. We will not get into the detail of this derivation, but the equation that if you are interested, you can look into any heat transfer book. The equation of fin will be given by the double derivative of T, that is temperature, equals 1 by A dA dx dt dx minus Hp by Ka T minus T infinity equals 0. The boundary condition at x equal to 0 is T equals T naught, that is given in the problem. And let us just say that at x equal to L, the T reaches T infinity, the ambient temperature. So the fin should be long enough to achieve ambient temperature at the tip of the fin. Base of the fin is T0 given, and tip of the fin is T infinity we are assuming. Under what condition it becomes T equals T infinity, that is a discussion more on heat transfer, and we will not discuss that here. We'll simply try to solve this equation. You can see that this equation with this sort of boundary conditions at x equal to 0 and x equal to L constitutes a very nice boundary value problem for us to think about. Here, of course, this A is the cross-sectional area of fin at certain x. So if I cut the fin, let's say over here, and look at the fin, its cross-section might look like this or might look like this. Whatever it is, the cross-sectional area of the fin is the A, which in general could be a function of x, and the P is the perimeter of the fin. So when I take a cross-section like this, if I take the perimeter of this section, that perimeter will be given by P. So the perimeter could be, if the cross-section is square, perimeter of 4 times 1 of this side. If the cross-section is, let's say, circular, then perimeter could be 2 pi multiplied by the radius of the circle. So this ODE, as I said, that this is applicable only for long fin because I am using this T equals T infinity as the boundary condition at x equal to L. But we will not worry about that part now. We will also not worry about the derivation of this equation, which comes in a heat transfer course. We will only see that how we can solve this equation. Now, this governing equation and boundary condition, in most cases when we are dealing with a physical problem, the first step is to non-dimensionalize. Once we non-dimensionalize, the number of parameters which appear in an equation will usually reduce. So in many cases, we try to non-dimensionalize the system. To non-dimensionalize the system, we have to define non-dimensional temperature, for instance. And we define in a way that we define theta as T minus T infinity divided by T naught minus T infinity. We believe that T naught minus T infinity will be the maximum temperature difference at any point. So we take this T naught minus T infinity as a scale. And in that scale, we measure all other T's. So at the end, theta will come between 0 and 1. It gives a very nice variation for us to deal with. So from this equation, I can write T equals T infinity plus T naught minus T infinity multiplied by theta. And then all this dt will come at T naught minus T infinity, which is a constant, multiplied by d theta. So I can come back to the governing equation and I can now write this as T is replaced by theta here. So I can write this is d2 theta dx2 plus 1 by a dA dx d theta dx minus h by ka theta. Now I bring a new variable z, which is given by x by L. L is the length of the fin. So you can see here it goes from x equal to 0 to x equal to L. When I do so, my dx becomes L into dz, and then I can go back to this equation and I can replace dx with dz. So I take this equation and I bring this d2 theta dz2 equals 1 by a dA dz d theta dz HPL square by Ka. You can see that this HPL square by Ka is already a dimensionless term. We can go ahead and non-dimensionalize area, etc., but that is not necessary for our present discussion, so I'll not go there, because we are going to drop this middle term quickly so that we can solve a simpler problem. The boundary condition at the same time also must be dimensionalized. So when we have t equals t naught, then you can see that from the definition of theta, if t equals t naught, the theta becomes 1, and at that point from the definition of z, this is z equals 0. Similarly, for t equals t infinity, you can see that from the definition of theta, theta becomes 0 for t equals t infinity, and this is at x equals L. So from the definition of z, this becomes z equals 1. So now that I have this equation, what I do, I take an assumption that a equals constant and p equals also constant, because a is constant, p will also be constant. We are simply assuming that the cross-sectional area will not change. Under this idea that a equals constant and p equals constant, this dA dz will be 0 because a equals constant. I can drop this middle term. I have d2 theta dz2 minus m square theta. M square becomes a constant, so m square is hp L square by Ka. This becomes m square. We keep this m square for two reasons. One is that we try to ensure that this is a positive, and the second is that keeping it m square helps us to do the analytical solution relatively easily. You can also keep it just as a constant like m. The boundary condition here is theta equals 1 to theta equals 0. The domain here is z equals 0 to z equals 1. So you can now see that after non-dimensionalization, the equations and boundary conditions look very nice. So let us see how we'll do this. Of course, an analytical solution is also possible, and whenever analytical solutions are possible, we try to do analytical solution. Even if we wish to do numerical solution, we try to do analytical solution as well, so that at the end we can validate our numerical results with the analytical results. If we solve this ODE analytically, I'm skipping the detail here, but if you don't remember it, you can consult any mathematics book. You will see that in general its solution will take this form: theta equals b exponential mz plus c exponential minus mz, where this b and c are constants which to be evaluated from the boundary conditions. To evaluate this b and c, we apply the boundary condition. For example, at z equals 0, this is 1, so that gives us b plus c equals 1. And at z equals 1, this is 0, so that gives us b e to the power m plus c e to the power minus m equals 0. So I can now solve in principle these two equations, b plus c plus equals 1 and b e to the power m plus c e to the power minus m equals 0 to get b and c. Please note that this m is simply HPL square by Ka, which should be given to us for solving this problem. If I solve these two equations, I get the following values of b and c. For b, it will be minus of e to the power minus m divided by e to the power m minus e to the power minus m, and c equals e to the power m divided by e to the power m minus e to the power minus m. You can see that we have all these terms are coming like e to the power m minus e to the power minus m, and you know when such terms comes, it is probably helpful to represent them in terms of hyperbolic function. So theta here comes as b to the power mz plus c to the power minus mz. I can use this b and c here, and it will come to us at e to the power m minus mz minus e to the power minus m plus mz divided by e to the power m minus e to the power minus m. And again, it's probably easier to represent them as hyperbolic function, and that is what we do here. So theta will be given by sine hyperbolic of m minus mz divided by sine hyperbolic of m. Okay then, so this is our analytical solution. We will use this analytical solution to see that how our numerical solution matches with this. What happens if I plot this analytical solution? Theta equals sine hyperbolic m minus mz divided by sine hyperbolic m. You see that we now have only one parameter here in our equation, that is m, and the z goes from 0 to 1. So we plot z from 0 to 1 in x-axis. Y-axis we have theta, and I can now take some values of m, and I can plot this function theta. Now you see that when m is large, we are getting a very strong nonlinearity here. Where m is small, the function is becoming more and more a linear type, which is understandable in this equation. You think about this equation: for m equals 0, theta will be linear. Similarly, for m tends to infinity, if m is very, very large, then you will see that this second term will be probably very large in most of the domain. So in most of the domain, theta will be close to 0, and you can see that when m becomes large, you can see that theta reaches 0 almost near z equals 0.5. So about half of the domain, theta is actually 0. Theta drops very sharply from 1 to 0 near z equal to 0, and region close to z equal to 0, only in that region this d2 theta dz2 will be important. It will be non-zero. But as soon as you go z greater than 0.5, you will see that this first term will become more or less equal to 0, and only the second term will dominate, which means that the second term will give us theta equals 0. Of course, these are more discussion of heat transfer rather than the numerical methods, but for all such problems, application of numerical methods are always difficult. So you try to understand the physical problems as much as possible from the analytical solution, simplified cases, so that we can validate our numerical solutions later on. Now, to solve this problem numerically, our goal is to take this above ODE and make it a linear algebraic equation Ax equals b. And how we are going to do that? The first step in this direction is something that we call discretization. The actual domain, what we have here, is a straight line between 0 to 1 in z. This is my actual domain. When we discretize, we assign finite number of discrete points on this particular line, and we are interested about solving our equation only at that discrete points. What happens between two discrete points are not our concern. In actual domain, of course, we have infinite number of points. Given any value of z between 0 and 1, this particular function, which is our analytical solution, will give us a value of theta, which is not going to happen in discretized domain. In numerical solution, we can only have solution at discrete points. And let us now see that how to discretize the domain to begin with. In a discretized domain, we will have these grid points here, and solution will come only at these grid points. These grid points, we have to give them a label, and I am giving this label at zi, I equals 1 to up to n. So we have n number of grid points here, and this n must be finite. We can take as many grids as necessary, but this n must be finite. How many are necessary? That will come to that discussion in due course. We can decide our grid fundamentally in two ways. These are one-dimensional grids, so these are easy. The first is the uniform grid. In uniform grid, the distance between two consecutive grid points, we keep it same, we keep it constant, this delta z, which could be a function of I. So for zi plus 1 minus zi, which is delta zi, which could vary over the domain. But if I keep it constant for all i's, then we call this grid an uniform grid. On the other hand, if at least one point this delta d varies, then it becomes a non-uniform grid. And as we have discussed, that once we decide the grid, we will have our numerical solution only at these discrete grid points, not in between the grid points. If you want the solution in between the grid points afterward, we have to carry out appropriate interpolation over these grid points. At the end, our numerical solution must be independent of the grids that we are taking. The grids are artificial construct. You can see in the original equation boundary condition, there is no such thing as grids. Grids are our artificial construct. We are using grids to have some numerical solution. So at the end, no matter how we decide our grid, the numerical solution should be independent of our decision, and this is something in computational literature we call grid independence. All numerical solutions should be independent of grids that we are taking, and we must test our solution for grid independence at the end. Now, once we discretize our domain, we have to discretize the boundary condition and the governing equation. And it can take three major routes. We know that there is this finite difference, finite volume, or finite element, three major methods that can be used to move further. In this course, of course, we will use this finite difference method. This will be our workhorse in this particular course, and other methods, of course, there are other courses. So if you are interested about finite volume or finite element, there are other courses we offer. You can look into it, where we use finite volume method and finite element method to solve by and large partial differential equations. How we generate these grids? This is very important in general in numerical simulations. But in the present case, of course, this is not difficult. We can take sufficient number of points. We can start with uniform grid and take sufficient number of points. Once we solve it, we have to test that if my solution is independent of grid size, and we can take one more grid, one different grid to solve it again and see that how fine grids are necessary to reach grid independence. Here, because we are using very simple grids, the complexities of grid generation are not discussed, but there are other courses where grid generations are discussed, and if you are interested, you can take some of those courses. For an exercise, you write a small program to generate a grid, only the grid. We are not going to solve it yet. generate only the grid. First is generate 100 grids. 100 grids means 101 grid points. So when we say grid, we assume that we are talking about the space between two grid points. So 100 grid means these are basically 100 blocks, 100 chunks. So these are 101 grid points. If we have one grid, it basically says we have two grid points. You can label them as 1 and 2. In uniform grid, this is super easy. In non-uniform grid, let's say you have same thing, 100 grids, that means 101 grid points, such that each grid is 1% longer than its left side grid. So if I take this delta Zi, this should be 1% longer. So this should be 1.01 times this delta Zi minus 1. Let's try this, and you can find a non-uniform grid. Non-uniform grid might be necessary because in some point where the gradients of the unknown variables are large, we want to use small grids. But in other parts where we know that solution will not vary much, just like we were looking at for large M, theta remains 0 for a large part of the fin. So in that case, we really don't want to take very fine grid in the parts where theta equals 0. It will not give us any more physical information. So in such cases, we can take non-uniform grid, which will save us computational time. So you can try writing a few lines of program and generate a non-uniform grid. So that's all for this lecture. Thank you, and I'll see you in next class.